In this video, we want to talk about the method of partial fractions. This is a technique that will help you evaluate integrals for some rational functions. Rational functions are polynomials divided by polynomials, and that's the kind of thing we're going to look at today. Well, let's start by looking at a motivating example, which perhaps at first doesn't seem like it's related to integration. But let's suppose that we wanted to add two rational functions together, say 2 over x minus 3 plus, and let's just put it as 1 over x plus 1, just to keep things simple. Suppose we wanted to add these two things together. The way to do it is to give them a common denominator. The first one, 2 over x minus 3, is lacking the x plus 1 from the denominator. But if I put it in the denominator, I have to put it in the numerator as well. And to this I want to add 1 over x plus 1. This I need to give a common denominator with the previous expression, and the thing it's lacking is x minus 3. But again, if you put that in the denominator, you have to put it in the numerator too. Well, now we can combine these. They have the same denominator now. So this is going to be 2 times x plus 1 plus 1 times x minus 3. And all of this is divided by x minus 3 times x plus 1. Let's simplify this. The numerator will just distribute 2x plus 2 plus x minus 3. And in the denominator, we have x squared minus 3x plus 1x is a minus 2x, then minus 3 times 1 is a minus 3. There we are. So this simplifies just a little bit. 2x plus x is 3x, and then 2x minus 3 is a minus 1 over x squared minus 2x minus 3. You might wonder what this has to do with integration. It certainly doesn't appear like it has anything to do with integration on the face of it. But the basic idea is that you want to integrate something that looks more like what we ended up with there. So suppose we want to integrate something. Let's say we want to evaluate an integral. And the integral we want to evaluate is 3x minus 1 divided by x squared minus 2x minus 3 dx. So this is the antiderivative, or the indefinite integral of a rational function. It's what we call a proper rational function because the degree on top is strictly smaller than the degree on the bottom. And it's something that maybe we don't know how to integrate. None of our techniques that we've discussed so far are really appropriate here. And so it seems like we don't know how to integrate this thing, but actually we do. And we're going to apply the same basic principle that we usually do. You start with an integral that you don't know how to compute, and you change it, you transform it in some way so that it's equal but looks different, like something you do know how to compute. And in this case, we want it to be equal to these two rational functions that we're adding together. That is to say, instead of integrating 3x minus 1 over x squared minus 2x minus 3, instead of integrating that, I'm going to integrate the thing that it's equal to, 2 over x minus 3 plus 1 over x plus 1. That's the thing that I want to integrate. This is what we call the partial fractions expansion. Partial fractions expansion. That's sort of a mouthful, so usually we abbreviate it as PFE just to make it a little easier to write down. But the point of the partial fractions expansion is that we can integrate the terms in it. We know how to integrate both of these. We can just do it term by term. The integral of 2 over x minus 3 dx plus the integral of 1 over x plus 1 dx. both of these can be done using substitution. In particular, on the first one here, if you let u be equal to x minus 3, then du is simply dx. So this becomes the integral of 2 over u du. And what about the second one? Now, let's not use u because we've already used it. Let's use w and say w is equal to x plus 1. Then dw is again dx. So this is going to be the integral of 1 over w dw. And both of these have elementary antiderivatives. 2 times ln of the absolute value of u plus ln of the absolute value of w plus a constant. And now we just plug back in 2 times ln of the absolute value of x minus 3 plus ln of the absolute value of x plus 1 plus a constant. Now, generally, you don't have to explicitly make this substitution. It's perfectly fine if you go straight from this line where you have the integrals of 2 over x minus 3 and the integral of 1 over x plus 1 and go straight to this last line, because this is the type of integral that you can probably do in your head. It's a substitution, but it's a substitution that's not so bad. At any rate, what we've done here is we found an antiderivative for our original expression. We started out with this expression 3x minus 1 over x squared minus 2x minus 3, which we didn't know how to integrate, but we rewrote it as the sum of these two simpler fractions, these two simpler rational functions. This was our partial fractions expansion, our PFE. And while we couldn't integrate the first original expression, we could integrate both of these parts. So these are partial fractions because each one is part of the whole. And each one of these parts is something we can integrate, and that gives us the final answer. And this, in a nutshell, is the method of partial fractions. Actually implementing it can be a little bit tricky because the type of the partial fractions expansion that you need to use depends on your original function, your original rational function. And that's what we want to talk about now. We want to talk about how to find a partial fractions expansion for a given rational function. Well, let's start with a given rational function. We want to integrate, or we want to evaluate the integral of p of x over q of x dx, where p of x is a polynomial and q of x is also a polynomial. So if you have a polynomial divided by a polynomial, that's a rational function, and that's the kind of thing we want to evaluate. So what we're going to do, we will find a partial fractions expansion for px over qx. Now, for the purposes of this, we will assume that px over qx is a proper rational function. What is a proper rational function? That's when the degree on top is strictly smaller. So the degree of the polynomial px is strictly smaller than the degree of the denominator, qx. Strictly smaller. The example we looked at earlier was a proper rational function. If it's not, then you have to use polynomial division, but we can talk about that later. So this is our basic assumption that we're going to use, because if you have something like that, then the claim, we can write px over qx as the sum of simpler rational functions. And what do I mean by simpler? I just mean things we can integrate. Things we can integrate. This sum of simpler rational functions, this is what we call the partial fractions expansion. And that's what we're going to talk about, how to actually determine what the partial fractions expansion is. So in our example, we actually worked backwards. We started with two fractions and added them together. That's what we had here. So we started with two rational functions that we added together to get to 3x minus 1 over, let me just copy it because we're going to need it down here so in our example we have this. And what we know is that we can write this as the sum of two simpler rational functions, namely 2 over x minus 3 and 1 over x plus 1. So again, let's just copy these. Let's just paste these here. So this is the partial fractions expansion. We can integrate these. And that's really the goal. The goal is to start with something that you don't know how to integrate, and then you rewrite it as something that you do. Now, what we did was backwards, because we started with these two simpler rational functions and we added them together. So how do you go from the complicated thing to the simple thing? How do you do that? So how do we go from the complicated expression on the left to the simpler one on the right? That's really what we want to address. And the basic idea is that you're undoing the addition of two fractions. So over here we have two fractions, and to add them together we gave them a common denominator. So what you want to do is you want to sort of tear it apart so it doesn't have a common denominator anymore. So we start with 3x minus 1 over x squared minus 2x minus 3. You factor the denominator, 3x minus 1 over, how's that going to work? Well, it's going to be x times x. There's going to be a 3 and a 1, and then it's just a matter of picking the signs the right way. So that's going to be a minus and that's going to be a plus. So what you can see here is that there are two factors. So what I must have started with was two original functions, rational functions, two fractions, and one of them had denominator x plus 1 and the other one had denominator x minus 3. So the idea is that there are two fractions that look like that, but I don't know what they are. So I know that one of them will have denominator x plus 1. I don't know what's in the top, so I'm just going to put in an as yet undetermined constant. Same with the second one. I don't know what actually goes in the numerator at this point. Let's pretend. Because I do, it's right up here. I'm looking right at it. But let's pretend that we don't know that. The idea is that we know that there's some function that looks like something over x plus 1, and another one that's something over x minus 3. And if I add them together, I'm going to give them a common denominator, which is going to be x plus 1 times x minus 3, which of course simplifies to x squared minus 2x minus 3. So let's actually do that. Let's start with these two unknown rational functions, give them a common denominator. So we have a over x plus 1 times x minus 3 over x minus 3. plus b over x minus 3 times x plus 1 over x plus 1. So what happens next? Well, you just pretend that you know what a and b are and just add them together. So you're going to have a times x minus 3 plus b times x plus 1, and all of this is over the common denominator, x plus 1 times x minus 3. And so now we just distribute a and distribute b. So on top we're going to have a times x minus 3a plus b times x plus b. And on the denominator we have, if we multiply this out, it's x squared minus 2x minus 3. Now we know that whatever this is, it must be equal to the thing that we started with. Now these are two rational functions, and they have the same denominator. So that means they must have the same numerator as well. They're equal, and they have the same denominator. So two equal rational functions having the same denominator must also have the same numerator. So using that as our guiding principle, that means that these two rational functions with the same denominator must have equal numerators. So 3x minus 1 must equal ax minus 3a plus bx plus b. So then the question is just figuring out what a and b must be in order to make this true. There are different ways to do that. Let's just group together this ax and bx. A plus b times x plus minus 3a plus b. So here on the left side, I have a degree 1 polynomial, and on the right side, I also have a degree 1 polynomial. Now, if these two polynomials are equal, that means that their degree 1 term must be equal, and it also means that their constant terms must be equal. That's the only way that you can have two polynomials be equal to each other. If two polynomials are equal, then their constant terms are equal, and their, in this case, linear terms are equal. So that tells us that 3 must be the same as a plus b, and also tells us that minus 1 must be the same as minus 3a plus b. So here I have two equations and two unknowns. I need to solve this system of two equations and two unknowns for a and b, and that's something that we can do. There are different ways to do it. For example, we could start with 3 equals a plus b, and we could solve this for b. So b is equal to 3 minus a. And then I could take this result and plug it into my other equation. So I have minus 1 equals minus 3a plus b, which is 3 minus a. So minus 1 equals minus 3a minus another a, that's minus 4a, plus 3. And now, subtract the 3 over to the other side, we have minus 4 equals minus 4a. The only way that can happen is if a equals 1. And then you take that and plug it back into this formula for b. So b is equal to 3 minus a, but that's 1, so b is equal to 2. So now we have our partial fractions expansion. We know that our original expression, 3x minus 1 over x squared minus 2x minus 3, is equal to a over x plus 1 plus b over x minus 3. And now we know that a is equal to 1 and b is equal to 2. So you just plug in a equals 1 here and b equals 2 there. And the net result, so the conclusion, is that 3x minus 1 over x squared minus 2x minus 3 is equal to a is 1 over, and remember it was over x plus 1, so over x plus 1, plus b is 2, and that is over x minus 3. So we just plug that back in. And that's how you find your partial fractions expansion. Let's describe the method in more detail. So what we're looking at is the method for finding a partial fractions expansion for rational functions px over qx. Okay. Now again, what we need the degree on px to be strictly smaller than the degree on qx in order for this to work. We can talk about what to do if that's not true in a later example. So we need the degree of the polynomial on top to be strictly smaller. Now, assuming that we have that, here's what you do. Step 1. Factor the numerator and denominator completely, and then reduce if possible. So really, you want this to be a reduced fraction. So cancel out any common factors between the numerator and the denominator. And then step 2 is, and this is the main thrust of it, we write px over qx as a sum. And this will be a sum of simpler fractions. Now, saying that is easy. The whole point is to write down exactly how to do that. And so that's what we're going to do. So case A, let's call it. So if the denominator qx has a distinct linear factor, so by distinct we mean that there's only one. So if we look in our example here, let me just look at this example right here. If we factor that, we get these two terms, right? So this is x plus 1 times x minus 3. These are both linear. These are linear terms, or linear factors. Linear just means degree 1. If you have a degree 1 factor, that's called a linear factor. So this linear factor degree equals 1. And distinct just means that it doesn't repeat, so you don't have a repeated factor. So if qx has a distinct linear factor, then the partial fractions expansion will have a term corresponding to it. So if the distinct linear factor is, well, let's say that the distinct linear factor is x minus a. So if qx has a distinct linear factor of this form, x minus a, then the partial fractions expansion will have a term that looks like a over x minus a, okay, where this a is a constant. So a is an unknown, at least so far, constant. I say it's unknown so far because the goal is to eventually figure out what that value is. So let's look at an example just to make it a little bit easier to understand what's going on. So example. Let's say you have something that looks like, we don't really need to know what the numerator is. The denominator, let's say it has something like x minus 2 times x minus 3 times x plus 4. just as an example. Now suppose that this is reduced, so none of those are factors of p. Nothing in the denominator is a factor of p. It's reduced completely. Then this is going to be equal to, well, what have we got? We have 3 distinct linear factors. For every factor in the denominator, you're going to get a term in the partial fractions expansion. And each one of these corresponds to a term in the denominator. So x minus 2 corresponds to a term, something over x minus 2. The x minus 3 corresponds to something over x minus 3, and the x plus 4 corresponds to something over x plus 4. And you put a constant in the numerator, an unknown constant, so a. Now for the second one, I can't use a again because a's already been used, b. And for the third one, I use c. It doesn't matter what letter you use so long as it hasn't been used already. So the idea is if x minus a is a distinct linear factor, then the partial fractions expansion will have a term like, as we said before, a over x minus little a. The important thing here is that a is a constant. We don't know what it is, but we'll figure it out. If you have 3 terms, so general rule here, general rule. Let's write it this way. Every factor in the denominator corresponds to a term in the partial fractions expansion. And if it so happens that that factor in the denominator is distinct and linear, then the term in the partial fractions expansion looks like that. Constant over x minus 2, or whatever the factor happens to be. So note, don't use the same letter twice. So I can't put an A here, and then an A here, and then an A here. They're all different. Well, it might turn out that they end up being equal, but you don't know that. They're undetermined, they're unknown, they're undetermined. It might turn out that some of them are equal, but you can't assume that from the start. So use an A here, a B here, and a C here, and if you have another term, use a D, and so on and so forth. Don't use the same letter twice. So this is case A. If the factors are distinct and linear, then the partial fraction expansions will have a term like that. Okay, that's the first one. Let's do B, case B. In this case, let's suppose that, so let's say if q of x has not distinct, but has repeated linear factors, say it looks something like x minus a raised to the n. So you have n of them. Then the partial fractions expansion will have the following n terms. So you're going to have n terms. There are n factors here, so you're going to have n terms. The first one is going to be over x minus a. And then the second one is going to be over x minus a squared. And then the third one is going to be over x minus a cubed, and so on. And you keep doing this until you get to the nth one, x minus a to the n. So there are n terms here. N terms. I know that there are n terms because my qx has a repeated linear factor and there are n of those. If there are n factors, you get n terms. Remember our general rule here. Remember our general rule. Every factor in the denominator corresponds to a term in the partial fractions expansion. So if you have a repeated linear factor that looks like x minus a to the n, there are n factors there. So those n factors correspond to n terms. Now what goes in the top? What goes in the top? Well, it's going to be a constant. So there will be a here. Well, let's call it a1, and then a2, and then a3, and then up to an. So A1, A2, A3, A4, those are all constants. A1, A2, A3, up to AN are as yet unknown or undetermined constants. So let's look at another example. So again, it doesn't really matter what we have in the numerator. And in the denominator, let's say that we have x minus 2 cubed times x plus 1 squared, for example. And again, let's assume that this is reduced as much as possible. So what is the partial fractions expansion going to look like here? Well, we have a total of 5 factors in the denominator. 5 factors. So if there are 5 factors, see there are 3 of them here, and there are 2 of them there, so there are a total of 5 factors. So that means we're going to have 5 terms in our partial fractions expansion, like so. Now, you start with the x minus 2, and it's going to be x minus 2, and then you're going to have x minus 2 squared, and then you're going to have x minus 2 cubed. One for each of these. And then you move on to the x plus 1 squared. So you're going to have x plus 1, and then x plus 1 squared, like that. So you have 5 factors altogether. So you have 5 terms in your partial fractions expansion. 3 of them belong to x minus 2. So you have x minus 2, x minus 2, x minus 2. And 2 of them belong to x plus 1. So you have x plus 1 and x plus 1. And then you just increase the exponent. So x minus 2 is the same as x minus 2 to the 1. And then you have x minus 2 squared, x minus 2 cubed, x plus 1 to the 1, and then x plus 1 squared, and so on. The thing that goes on top is just a constant. So let's just do it this way. A, B, C, D, E. You could do A1, A2, A3, A4, and this could be A5 if you wanted. The only reason I use a sub n here, the only reason I use subscripts is because I don't know how many there are. I know that there are n, but I don't know what value n has. Here, in this case, I know that there are 5, so I can just do A, B, C, D, and E, the first 5 letters. But you could also use subscripts if you wanted. All right, so this is our partial fractions expansion, and you'll notice that there are 5 terms. So anytime you have a repeated factor, this is what you do. You write it out in this way. The next thing you might have is you might have, so if Qx, let's say, has an irreducible, I lost my E, irreducible, or my L rather. If Qx has an irreducible quadratic term, let's say it's something like x squared plus a squared. So if Qx has an irreducible quadratic like that, then the partial fractions expansion has a term that looks like, so what's this going to look like? Well, it's going to have x squared plus a squared on the bottom. That's the factor. So what goes in the numerator? Well, the numerator is not going to be constant in this case. Here you have ax plus b. So the idea here is this is degree 1. Degree 1 with unknown or undetermined coefficients. You might expect a constant, but it's not a constant, and the reason for that is that the thing in the numerator always has to be degree 1 smaller than that in the denominator. Let's write that down. So the degree in the numerator is 1 smaller than the degree in the denominator. This is always true. It's true here because you have degree 2 in the denominator and degree 1 in the numerator. If you go back to our first expression, our first example, we had distinct linear factors. So here we have a degree 1, so the numerator is degree 0. In our second case, these are all factors that are degree 1. So there's a degree 2 there, and a degree 3 there, and a degree n there, but the factors themselves are all degree 1. So the numerators have to be 1 degree smaller, or 1 degree fewer, if you prefer. So when I say the degree in the numerator is 1 smaller than the degree in the denominator, what I really mean is the degree of the factor in the denominator that gave rise to the term in the first place. In the partial fractions expansion. It's always easier to see this if we look at an example. So let's say we have something like, again, we don't care what's in the numerator, but in the denominator, let's have x minus 2 times x plus 3 squared, and then let's put x squared plus 4. So we have a distinct linear, we have a repeated linear, and here we have a distinct irreducible quadratic. If this were a minus, you'd be able to factor it, but it's a plus, so it's irreducible. You can't factor it, at least not over the real numbers. So what is this going to look like? Well, for every factor in the denominator, you're going to have a term in your partial fractions expansion. So this is going to be something over x minus 2 plus, and then it's something. Here we have x plus 3 times itself. So x plus 3 plus x plus 3 squared plus, and then finally we have x squared plus 4. So notice that here you have 4 factors. It might look at first like there are 3 factors. You have 1 factor, 2 factor, but there are actually 2 factors here. So you have a total of 4 factors. So that means you're going to have 4 terms in the partial fractions expansion. And what goes in the numerator? The thing that goes in the numerator is always 1 degree smaller than the factor that gave rise to it in the first place. So this is degree 1, so the thing above it is degree 0. This is degree 1, so the thing above it is degree 0, or constant. X plus 3 is degree 1, so the thing above it is constant. Now we have an x squared plus 4, which is degree 2, so the thing above it is constant. So we can't use a, b, c, so we say the next letter is d, so dx plus e. Again, don't reuse letters. If you've already had an a and b and a c, then you don't want to use those again. So that's your partial fractions expansion. Now the other thing that might happen is qx might have repeated irreducible quadratics. And in this case, then we have a term in the partial fractions expansion for each factor. So, and then we sort of combine what we've seen before. So if Qx has a repeated irreducible factor like x squared plus a squared, and then it's raised to the n, then we have in the partial fractions expansion, something like x squared plus a squared in one factor, and then x squared plus a squared raised to the 2 and another factor or another term. Then the next denominator will be x squared plus a squared cubed, and you keep going until you get to n. So it's x squared plus a squared to the n, just like when we had repeated linear factors. Now it's not repeated linear factors, it's repeated irreducible quadratics. We have n factors here, so again, let me write that down. N factors, so that means we have n terms. And the thing that goes in the numerator, again, is it's going to be 1 degree smaller than the factor that we started with. So the original factor is degree 2, so the thing in the numerator is degree 1, so we're going to have ax plus b. Now again, I don't know what value n has, so let me give these subscripts. So a1x plus b1, a2x plus b2, a3x plus b3, and so on until you get to anx plus bn. Now, hopefully, with any luck, you're not going to have a very large n in this case. We'll try to stick to cases where n is equal to 1. So we'll try to avoid this case d and stick to this earlier case c. But it works the same basic way. So if you have an example that's px over, and let's just say we have x squared plus 4 squared times x squared plus 9 squared, then there are 4 factors here. So you're going to have 4 terms. And the first two come from x squared plus 4. So you're going to have an x squared plus 4 and then an x squared plus 4 squared. And then the next 2 come from x squared plus 9. So it's x squared plus 9 and then x squared plus 9 squared. And what goes in the numerator? Well, in every case it's degree 1. So you'll have ax plus b, cx plus d, ex plus f, gx plus h. Now, something like that's going to be actually rather difficult to work with, but that's the basic idea. This tells you, so this method tells you the form of the partial fractions expansion. But then you need to solve for any of these constants, any of the unknown constants. And that is an arithmetic algebraic problem, but that's usually the most difficult part. Once you have that, once you have the partial fractions expansion, then you can integrate the original px over qx by integrating the terms in the partial fractions expansion. But before you can do that, you need to solve for the unknown constants. And that's what we're going to do in our next video.